All right. Thank you all for coming. I think this is the third seminar we host at Ecumen. Today's we have the opportunity to hear Dr. Raji, who will be speaking a little bit about model complexity and reduced order models in high performance MPC. I think I met you at Atlanta earlier this year, and your publication at the time caught my eye, definitely. For the rest who don't or who are not familiar with Dr. Raji's work, Ayub Raji is a postdoc researcher in mathematics and computer science at the University of Modena and Reggio Emilia in Italy. As a researcher in the HYPERT lab, the High Performance Real-Time Laboratory, he's responsible for the R&D of planning and control algorithms for autonomous driving solutions. His main research focus is on model predictive control and another for autonomous racing and bringing physical AI to achieve superhuman performance. Leading the Unimore racing team, he participates in the main international autonomous racing competitions on full-scale race cars, full-scale F1 race cars, the Abu Dhabi Autonomous Racing League, and the Indy Autonomous Challenge. So without much further ado, Ayub, the floor is yours.
Hi, thank you a lot, Mika, for the really nice introduction. I will share my screen. Here we go. Okay, and I will start the presentation. So yeah, hi everyone. Today, as Mika said, I will present this seminar about model complexity and reduced order models in high performance MPC. Really glad to do this seminar and glad to have no new. I hope that this could be useful also for you and could maybe create some connection for the future. So yeah, as already been said, I'm a postdoc researcher at HYPERT Lab, a laboratory in the computer science and mathematics lab in University of Modena, Reggio Emilia. My background is more about computer engineering, and then I followed during my master thesis a bit the robotics and autonomous driving, particularly racing. Then during the PhD in mathematics and computer science, I focused more on MPC. Based on for planning and also control for autonomous racing. My main research focus is, let's say, on MPC and for racing, and in particular to close the gap between the human level and AI, physical AI and autonomous race cars in at least lap time performance, and then in the future probably we'll see how it will go. Yeah, please make sure to follow my works if you think that it's interesting, and feel free to connect. So yeah, my little bit of background about the lab. Our lab is focused in let's say origin is about high performance scheduling embedded systems. Then in the years we moved more on applications related to autonomous driving for normal new urban driving, but as well for racing scenarios, and in particular focusing on complex workload intensive tasks, moving them to really embedded platform, NVIDIA based, and etc. This also led us to open also startup with the same name of the lab, HYPERT. If you want to check more, so we moved this kind of application also in the industry, in logistics, and so on. But yeah, as I previously said, my background started, let's say, I applied my background in robotics and autonomous race cars, starting from really scaled vehicles like the one that you are seeing now. This is like a 1/10 platform. It's used basically to, let's say, prepare students and researchers in a really economical way. It's about 2K more or less, 2,000 euros, 2 or 3,000 euros to build it. And it's easy because, of course, you can crash it without any big expenses, and this is an awesome way to learn. This is where I started. Then in 2021 and 2024, the two main, let's say, autonomous racing leagues started. One is the Indy Autonomous Challenge, the other one is the Abu Dhabi Autonomous Racing League. And here the focus is about putting wheels robots, autonomous robots on real full-scale vehicles. These are the same platform that I use for professional championship in the Indy Lights, which is the second championship in the USA, and the Super Formula, which is the main championship in Japan. And after the F1 is basically the fastest Formula race car in the world. So yeah, this is quite a short recap of what happened like in the last race, to give you, let's say, more or less an idea. We've been able to race with 6 cars. We were the fastest during the qualifying. On the sprint race, we've been passed by TUM, which is from University of Munich. Then we've been able, let's say, to also pass them, as you will see really soon, which is something really interesting, because in the years we improved a lot the performance, but let's say that it passed a lot of time since we've been able, let's say, to see some active overtakes and something like that. And this time we've been able, let's say, to do something, accomplish something really great. And also consider one thing, that this competition, the last year, the gap between the human and the AI, physical AI, and autonomous race car was about 10 seconds. This year was about 1 second. So we reduced 9 seconds just by a year. And there would have been, let's say, even better, let's say, performance, but we were limited by time. I'm sure that for the next race we'll be really close to that, and that will be great. Of course, it's racing, and not everything ends always in the proper, the perfect way. Unfortunately, at the 12th lap, when we had to lap again another slowing car, it didn't, let's say, behave correctly. It stopped almost in the middle of the turn, while we were overtaking the TUM car, where the other car, the TUM car, was approaching us, and this led to a crash. This is, of course, unfortunate. It was really a bad result for final result, but we were still proud of what we did. It was really the first time that any researchers, labs and teams have been able to make some kind of show. But this is also part of the learning. As you will be able to see, it was really an edge case scenario that we should also manage better by us, but also the race control, the other teams, and so on. But this is part of the game and part of the research. So yeah, going ahead and going more practical, now that I showed you a little bit what I'm doing and what was my background, let's start about MPC. I know that several of you have, let's say, good background on robotics, but it's still a good idea just to give some references on history and basically the state of the art. So yeah, as you may know, the evolution of the MPC started more or less about the 1970, where the MPC were used more on process control. So like in industry related to pharmaceutical, chemics, and so on, where the dynamics is quite slow. There's no need for high computation, for really extensive computation. So it was something feasible, and also using linear MPC through, let's say, until the 2000. After that, we know that the automotive industry have been really raised and increased a lot the progress, and as well the automotive control, so the control aspects on the automotive. And the last, let's say, from the 2010, more or less, a lot of industries and companies started to include, let's say, MPC, not just PIDs and classic controllers, but also MPC, more on explicit and hybrid MPC, where it's possible, let's say, to create, for example, lookup tables without relying on solvers and high computational resources. Then this moved as well in the aerospace systems, in drones as well, using linear time varying MPC, so having like a non-linear dynamics, but moving to linearizing the system. Then this has been also integrated in the IT systems, informatics and technology systems, using distributed and decentralized MPCs. So communicating, having, let's say, shared control, shared resources management using MPC. but as well in energy, in finance, and so on, using also the stochastic MPC, which is like a kind of MPC where instead of modeling accurately each part of the system, it's able also, let's say, to model the disturbances of the system through a probabilistic function, probabilistic modeling of this kind of noise and disturbances. Then in the last, I will say 10 years, the focus for MPC have been moved to putting everything in embedded systems and moving also the optimization part to be, let's say, compliant with the needs of the embedded industry. So industry, not just automotive, but robotics and so on. And this moved, let's say, a lot of work for solvers. Like there have been a lot of solvers used in the market, free open source ones and commercials that have as a focus, let's say, more specific and tailor-made for really, let's say, for example, really short matrix-based MPCs problems or really large problems and so on. Today, of course, the focus is moved a little bit more on machine learning, and as well, this moved as well in MPC. With really a lot of data-driven MPCs solutions and proposal from the research, which could be like, for example, learning-based ones, probabilistic statistics one, but also reinforcement learning-based ones. So this is, as I was starting to say, is the trend. That's of course you know it, of course, working on this field, that the trend is about using AI of what we all call or they call AI-based solution for everything. So starting from end-to-end neural networks that have been a little bit old nowadays, to reinforcement learning or hybrid solution where reinforcement learning is approached with MPC in order to try to let's say reduce the issues about the complexity of the models that sometimes researchers, but also industry, they don't want to spend enough time to find the model and tune the model and so on. So they try to associate with also a reinforcement learning part in order to, for example, learn the model and so on. But the question is it really the correct path for everything? And to be honest, this is a little bit more a philosophy that more or less I agree with Jan LeCun. For sure, you may know him now. He works in Meta, but he's been one of the pioneering computer scientists applying researching on AI and neural network based solutions. And he was quite let's say clear in 2016 when he said that that for the majority of the tasks nowadays in robotics, MPC solution it's enough, because in the end, if you really have a decent and good world model, and usually this is the case, should be enough to solve tasks without any big trouble. Because of course, RL solution and neural network based solution requires really a lot of data, and we still, let's say, not been able to completely satisfy the topics about safety of AIs. Of course, we are moving towards this using exploiting, for example, simulations, focusing on having really, let's say, the digital twins of everything, of our robots and stuff. That will be probably the way, but this is still let's say a debate about if it's the right way, right path for everything. And let's say that is still open, but this is my philosophy. I think that for the majority of the tasks, we still don't need this kind of approaches. Of course, for the future, we'll mention it a little bit in the later. A mix of these two approaches could really bring really, let's say, satisfying results and let's say being able to accomplish what we are still searching on. So after this quick introduction about MPC and let's say this philosophical parenthesis, I will focus a little bit on the application that it's based on my research. So MPC applied to autonomous racing. As you already know, let's say for sure the scheme, the design of a really generic, high-level scheme of an MPC. You have the plant. In this case, is the vehicle. We have the vehicle model. We have the optimizer and the solver. We have the references that, in this case, for this kind of vehicles are some trajectories. So, for example, a path and a speed profile in order to be followed by the car. And this model should be, let's say, good enough in order to predict correctly the next horizon errors. And this then it's put, let's say, into a solver in order to find the future inputs and the solution, constrained with some particular, let's say, limits and bounds in the states and the input. In our particular case, what we use, I will quickly give, let's say, an introduction, is a particular model called single track model, where you lump the two front wheels into a single wheel. The same thing for the real wheels to simplify the model, and we write it in curvilinear coordinates. So instead of Cartesian coordinates, we use curvilinear coordinates, or known as well for as Frene coordinates. The inputs usually are steering angle, throttle, brake, or otherwise we can use as well steering angle and acceleration, as we'll see in shortly. And as states of the system, we have like the positions, the heading, the speeds, considering both the longitudinal and lateral speed, and the yaw rate. So then, yeah, as I said, as reference, we usually have a trajectory. And as solvers, usually this single track model is, we'll see it soon, is a non-linear model, but usually it's linearized over a region. In this case, in this particular region, the linearization is not done in a particular steady state point, but it's done through the previous horizon, the previous solution of the MPC, making, let's say, the linearization more accurate. In particular, we are using a HPPM solver, which is a ad hoc, let's say, a tailored optimization solver, based on the interior point model. Interior point method, sorry, and the main focus is about small matrices problems like the one that we have, where we have really a limited amount of states and inputs. We have a horizon length of more or less 2.6 seconds, with sampling times, so steps of 40 milliseconds, and running a frequency of 10 milliseconds. So at each 100 Hertz, we run the execution and we apply the command. So it's a really fast execution and system to actuate. As I said before, this is, let's say, the model. I will not go too deep, let's say, in the formulation. I don't want to be boring, but just to give you an idea. So we simplify the model in this way. So from the two wheels on the front and the two of the rear, we lump them to a single wheel. This is quite a common one, called single track model or bicycle model. We model and we include several aspects and dynamics. So the longitudinal lateral dynamics, forces, the forces due to the banking, so the road, the one due to the let's say the combination between the longitudinal and lateral, the curvature, and so on. In particular, for the lateral forces, what we use is a formulation of the tires called Passeika magic formula, which is not really, let's say, a physical based solution, but it's more a heuristic. This is also the name, this is why it's called a magic formula, because basically the dynamics, the characteristics of the tires, because basically in our case, the lateral forces, but also the longitudinal forces are generated through the tires. And this, the tires has a certain dynamic which can be modeled with really several complex tire models, but with this magic formula, with just 5 parameters, 5 microparameters B, C, D, and E, it's able to fit the model. So here you can see in the blue region that there's the data that we want to fit, and the orange one is the model that we use to fit. And of course, also the data is quite noisy, as usually is in this kind of environments, but this model is more or less able, let's say, to understand the fitting. We add also some particular aspects like some offset due to the lateral forces, some shifts, and so on. But as I said, I don't want to be too boring about this, the model part of this specific region. I will share later, let's say, some more interesting parts related to reducing, let's say, the order model and simplifying or keeping, let's say, complexity without having too many states. Regarding, let's say, the cost function of the MPC, as I said before, of course, it will be, the model is discretized using Runge-Kutta method. For the cost function, we have a part that, let's say, weight and incentivize the progress rate. So it weights it incentivizes the vehicle in order to move forward. We have some path following weights, so regarding the lateral offset and the heading. So basically, it's the lateral error and heading error, and then also a velocity tracking weight, so that we weight how much we want to follow, our reference on the velocity. And of course, then we have some inputs regularizers in order to regularize and the inputs and their change of rate. And we have also like a regularizer of the rear slip angle, which means that basically we say to the car, to the MPC, to make some action that don't, let's say, create too oversteering. So not being a really dangerous, do not, let's say, move to dangerous situation and actions. So regarding about the optimization problem, yeah, we solve this. We try to minimize this cost function, including also some constraints. For example, the racetrack. The racetrack has some boundaries, some track lines. We should respect them. We do it as a soft constraint as well as for the lateral forces, the tire forces. We have some soft constraints for this. Why we use soft constraints? Because in this particular field, but also in other, let's say, real world applications, it's really difficult to create, let's say, a solution that never exits, never reach the and overcome the bounds. One thing is a system that you can put on your table, on your desk, or a lab, and you are able, let's say, to limit it. That's a thing. But when the model mismatch increases, when the environment changes too much, etc., having a bound on such a kind of critical application, it's really dangerous, because it means that you could put the optimization, the solver, in an unfeasible solution. So this is why for some aspects like the track and also the respect of the dynamics of the tires, we use some soft constraints, and we make sure to make some appropriate weights in order to respect them. Then we could also, let's say, include some bounds on the velocity or other aspects as well, the physical bounds. This particular then solution is solved using HPPM. As I said, is a tailor-made solver for MPC, and CPP at Decogen, which is a tool in order to generate, let's say, automatic differentiation libraries and code in order to have, let's say, to have a low, let's say, computation about the differentiation. So not all the differentiation is done online. A part of it is done offline. So this being said, as an introduction to the MPC on this application, let's get into how we enhance the model and keep the accuracy without putting too much complexity, so without increasing the states and so on. For this case, I will show you, let's say, some examples of a paper that we published some years ago, and we also talked about in the let's say, the system paper in ICRA. So basically, for sports cars, what you have the real wheels that generate some. You have, let's say, the engine and the torque, and it's the traction is on the rear. And there's a differential, which is a system that it's able to put, let's say, a different, let's say, torque and different power between the rear, the left and the rear, the right tire. For example, in this particular vehicle, which is the vehicle on the India Autonomous Challenge, there was a locked differential. This means that when the differential is open, which is common on normal urban cars, it means that when a certain tire slips, has some slip, the other one it's blocking, it's not moving, so they are not, let's say, moving at the same speed. Instead, for a lock differential, it means that both the axles, both the left and the right side, so the left and right wheels are moving together. This is something, let's say, that creates a certain moment. It creates an additional yaw moment to the dynamics due to the longitudinal forces. So when we accelerated, we also generate some yaw moment, an additional yaw moment, and not just the one created by, let's say, the steering and so on. And this yaw moment makes the car turns more or less in the rear axle. This is a really, let's say, complicated, in theory, it's a really complicated dynamics to capture, to include a model. But what we did, and there are other references in the literature, is to use what we call the 3-cycle model. So we instead of the bicycle one, we included the 3-cycle model, but the point was to not add additional states that into the system, to the formulation of the MPC. But still, we want to model differently the rear and the left tire forces. And this also helps also to avoid, let's say, high cornering stiffness, which means that the model, if we had to add some states and etc. for modeling these kind of aspects, it will also create some numerical instability because the problem will be really stiff. And this is also simpler than other more complex models. For example, there are also models, including the 4 wheels model, which could solve this issue, but they are more complex and heavier for the MPC potentially. So what we did, we added to the the equation that we saw before, the additional yaw moment, so to the yaw rate equations of motion, so the differentiation of the yaw rate, we added the locked differential yaw moment, which I will quickly, let's say, explain how it's represented. And instead of having the throttle and the brake, we have an acceleration, a drive input that we call drive, which basically represent the acceleration of the vehicle. So we don't include the throttle and brake directly, but acceleration. We'll get back in this to this point. So we have as inputs the change of rate of the steering wheel and the change of rate of the acceleration. So basically the rate of change of the steering and the jerk. And then the other ones are basically the longitudinal lateral progression, so in Frenet coordinates, the heading error, the longitudinal lateral velocity, the yaw rate, and then the actual steering and the actual acceleration. In order to do this, we create, let's say, we try to find this, we model this yaw moment that it's derived from rotational equilibrium of the real axle in the z-axis direction. This, instead, the longitudinal forces, it's from the dynamics of the, for example, the commands, but as well from the locked differential contribution. So we have the normal, let's say, traction dynamics plus the contribution from the locked differential. This locked differential, it should be, let's say, find using the Passaica tire model, longitudinal model, where there's a slip ratio. The slip ratio, it's basically a ratio between the current velocity on the wheel. So, for example, the wheel odometry, so that you have an encoder on the wheel, and the current vehicle velocity instead. So when there's a mismatch between these ones, it means that we have a slip ratio. So there's differences between the real velocity and the one on the wheel. This means that basically the car is slipping, is not creating, let's say, it's not putting all the force, all the torque to the ground. But the slip ratio depends on the ideal speed of the real wheels, taking in account the geometry and tax layout like curvature and radius and so on. As I said, yeah, we use, let's say, this. I don't want to, let's say, go exactly deep and down on these particular aspects, but what we do, we have like a particular dependency to vertical load and lateral transfer, so really a little bit more complex aspect of vehicle dynamics. And the issue is that the actual moment that we want to add, so the additional yaw moment that we want to add, depends on the previous integration step. So basically, the yaw moment that we see here depends on the previous yaw moment that we had. So basically, in our MPC design, it means that in the horizon, in the prediction, you need to estimate this value, but based on the value that you had in the past, the previous steps of the horizon. This basically, it means that we would, let's say, need to add the state. This is let's say exactly the point. But instead, what we did is that as I was saying, that adding an additional state will increase the computational time. Instead, what we can do is to add an additional independent variable. For who is not familiar with this aspect, independent variables are some variables that are not states or inputs, but are constant and is like basically a vector that you can pass to the MPC that you calculated it before the optimization. So basically, for example, the curvature, you know the curvature of a path that you want to follow. So you pass directly the curvature of that path to the MPC. So you have a static, let's say, a vector for each time step of the horizon. You have a certain value. Or for example, it could be the road. The road could have like a slope, and you already know, let's say, what is the angle of this slope. You can directly pass this vector to the MPC without having the state. So what we thought about is let's add this yaw moment as an additional independent variable, and we can calculate it before running the MPC using the previous MPC solution state. In this way, we can then calculate it and passing the yaw moment to the MPC. This is, of course, a simplification because it means that we are using the previous iteration of MPC to calculate the state. That, of course, it will be different in the next step of the execution. But this is an acceptable simplification, assuming that the MPC should not produce, let's say, an updrop change compared to the previous solution. This thanks to a stable model, but as well also a well-posed optimization problem. This, for example, is solved using a sequential quadratic programming method. So it's quadratic programming because we want to keep, let's say, positive defined problem, but also sequential quadratic method. So it means that we run multiple iterations of the optimization. So in our case, 2 or 3 iterations. This means that we usually converge and stay close to the convergence. The other aspect is that also we run at high frequency, 100 Hertz. And also that we have like some regularization terms in the cost function. This helps, let's say, to keep, let's say, the solution smooth. So basically, we focus on having a smooth solution that doesn't change through time in order to make this assumption acceptable. And the other aspect that was important in this example is also the discretization of the MPC and the model. So doing the discretization at a sampling of 40 milliseconds, which is what we used, let's say, in the past without this problem, or in other models with a Schusen integrator, for example, Euler or Runge-Kutta. We saw that the stability of the system was able, let's say, to be that the system been able to stay stable, running at least at 8 meter per second, following at least a minimum of a maximum, sorry, of 8 milliseconds of sampling time. So this 40 milliseconds was not acceptable in order to keep, let's say, the model stable and the optimization stable. This has been done, let's say, easily by, let's say, pole placement and understanding, let's say, the stability of the system. So therefore, sampling, the issue is that sampling with using 8 milliseconds to each step of the MPC horizon is something that is not feasible. It's not suitable for solving a real-time optimization problem. So indeed, we were using 40 milliseconds sampling steps. What we did in order to solve this issue is that basically we introduced this kind of concept of micro steps discretization. So basically, usually when you do the discretization, you have your next steps that are depending on the actual step, the actual state of your system, and the input and the delta of time. But this time, what we do is we do like micro step discretization. So for each discretization, we do further micro steps. So this delta t is let's say, divided by a h divisor, a time divisor, which has been chosen in order to reach, let's say, divided by h that 8 milliseconds. So this means that you are basically doing you are keeping the same input through a shorter amount of discretization, and then in this way you discretize the model more accurately. This doesn't mean that you are doing the optimization at this kind of discretized sampling time. You are still doing, let's say, the optimization at for example, the 40 milliseconds, but in order to discretize and linearize the system, we used these micro steps that helped to have a more stable system. So this is then used, of course, by the optimization, the MPC, in order to find the optimal solution. Another interesting aspect that I mentioned before was to introduce, let's say, to produce later the throttle and brake commands from the longitudinal acceleration requested by the MPC. So basically, in the past, what we did, also other, let's say, solutions, other researchers are using, are directly putting the throttle and brake, for example, inputs to the MPC. Instead, in order to reduce the number of states, but as well the inputs, we put the acceleration, so the longitudinal acceleration, which is basically the dynamics that is generated by these commands, as state as of the MPC, and then as the input, just the jerk, so the derivative, the rate of change of the acceleration. Then after that, we calculate the throttle and brake using a feed-forward action, with having, of course, a bit of knowledge about the engine, the brake, and so on. Then we use, let's say, a PI controller in addition to the feed-forward in order to reduce the mismatch. This is, let's say, another strategy in order to have a reduced order model MPC. So basically, you reduce as much as possible, let's say, the state and the dynamic that you can then potentially convert and pass using a more, let's say, a simpler, less complex solution, which could be like a feed-forward and PI strategy. So basically, it's about having some levels of complexity in your control system, and having, let's say, a design that mix optimization controller like MPC, but also more basic controllers. This is just to give a quick idea of, let's say, the level of accuracy. This is with these three cycle models. With this updated model, we reduced. This is an old example, but still valid. The lateral error, you see that with the old model, we let's say did more than half meter of lateral error, while with the new model we stayed, let's say, within the half error. This is also even more visible in this case. And yeah, and then there's also with further, let's say, tuning and parameter fitting, have been able to reduce even higher. You can see that in this particular region, when there's more mismatch, these dynamics that I talked about the lock differential was more visible. Thanks to this model, we've been able to have, let's say, almost half of the lateral error that we had before. And then this is, let's say, just a demonstration that with this model we've been able also to reach the limit of the vehicle. So it means that basically we are not we are also able, let's say, to reach the goal of that nominally in a race car you are trying to achieve. So one of the last points that I want to mention is about the executional time. So in this case, you will be, let's say, interested as well to understand what is the executional time of this kind of application and solution. This is quite different platforms. This is let's say high performance computers. The first two ones, one is from Anautera, which is from DSpace platforms, which has, let's say, extensive computation, and then these Xavier NX and AGX are NVIDIA based with lower performances and with limited frequency of for the CPU. Nevertheless, we've been able with the MPC to keep, let's say, below the 100 hertz, let's say the 10 milliseconds let's say limit that we have due to the 100 hertz let's say restriction from the low level control. So using the high performance computing, of course, we are below 5 milliseconds. With the AGX or even the NX, which is lower than 2 gigahertz, we always stay, let's say, below 10 milliseconds. There are some spikes. These spikes are basically just in the results due to, let's say, not properly allocate some cores and threads to the processes. We've add new, let's say, some new results. We dedicated a little bit of effort on this topic and giving, let's say, the particular core and thread to the MPC, we've been able to have a better performance and let's say a more stable performance. And this is, let's say, just a box plot understanding, let's say, more or less, which is the trend of this. So this has been able, this has been possible thanks to using the HPPM, which is this high performance area point method, which is an open source solution tailored for MPC application, using, let's say, also the fastest available mode in this optimization in solver, because there are different models rather than the robust one, since the problem which we solve is, let's say, not too complex. It was already, let's say, well defined. We've been able also to achieve these times, execution time, thanks to generating, let's say, offline some automatic libraries, differentiation libraries, to perform offline some part of the differentiation, reducing then the online executional time. And then also, as explained, having less states and less inputs, which means small matrices, therefore low computational time needed to perform the factorization and the discretization and finding a solution. The last part, which is, of course, one of the most important, is about the model, that, of course, we had to find an accurate enough model, not making, let's say, too complex, but in the end also having an accurate reference. This is something that I didn't mention. It will need me more time. But the other point that is particularly crucial also to have a reference that it's quite close to the not that close to the optimal solution, but towards the optimal solution. This means that, for example, in our case, we are giving as reference a certain path, certain speed profile. The speed profile, that path should be something feasible, more or less already feasible. If we give, for example, the car is at 10 meters per second, but we directly give as reference 100 kilometers per hour, for example, of course, we have like a huge, let's say, gap, and this makes, let's say, make us too far from the optimal solution. So what we can do instead, we know more or less the limits of the longitudinal possible limits. We know that we cannot do more than a certain acceleration, so we calculate a feasible velocity, and for each step, for each horizon of the MPC, we give a feasible reference, velocity reference. This will reduce a lot also the executional time. So, and also because in this way, the optimization will stay already closer to the optimal solution. So yeah, this is, let's say, almost all from this seminar. Quite quickly, let's say, to open also for potential question and so on. The last point is about what are the current open topics. As I previously mentioned, now, let's say, the trend is to try to understand if physical AIs, like how nowadays we call as well MPC and this kind of approaches are enough, or we need to move forward to reinforcement learning based ones, neural networks and so on. This is, let's say, a little bit the question, because we have, let's say, some example, for example, for drones. There are autonomous drones that are faster than humans, and they are all, let's say, based on reinforcement learning and neural networks models. But for really, let's say, safety critical aspects like cars, race cars, robots and stuff like that, to actuate these kind of robots, it's still an open question, and this is something that is still in involvement. The research is going towards a mix, so mixing the two solutions, trying to have, let's say, a model based control together with our reinforcement learning and neural networks part. But the open topic is to find the correct balance between these two aspects, and this is still something really open. The other aspect that is moving a lot is about the simulation, so trying to really close the gap between reality and simulation, because this will help us to create like different scenarios similar to the reality, that the reality changes a lot, and in this way we could be able to train our networks, models and stuff easier in simulation before going out in the real world. So yeah, that was all from my side. Thank you for your attention, and I'm available for any open question.
All right, that was amazing. Thank you. And we have about 10 minutes for questions. Everyone, if you go down below to the right, find the 9 dots, look for Q&A, and you're gonna see the place where you can ask all the questions that you may want to ask you. We already have a few, and they are in votes, so we'll start in order. So our first question is about model identification. So the exact question is, how do you perform model identification for both the car and the tires?
Yeah, what we usually do is that we have some instruments, some sensors that are able to gather, let's say, the data about the lateral velocity of the vehicle. There are like optical sensors in order to have that, and that give you, let's say, a ground truth idea of this dynamic. But we also in this last years we worked also on a cheaper solution, because these optical sensors are really expensive. They cost like 30,000 euros. But we've been able also to use some cheaper sensors like lidars, cameras, and radars, even radars that are, let's say, nowadays easy, and they are also in the normal cars. We get data from that, we exploit and we split, let's say, the velocity vector, and being able to extrapolate the lateral velocity. Once we have the lateral velocity, we can then let's say have we can have the lateral, let's say, dynamics, and fitting the tire model on that. We can able to generate the slip angle, so the slip of the tire and the forces. This will, let's say, simplify a little bit the model identification. Another important aspect that we consider is that we don't model just the tire, but we model the whole axle, so the front axle and the rear axle, the whole characteristics. This simplify also a lot. We don't have, let's say that the whole dynamics of the suspension, etc., and the geometry is included already here. So when we get from the data the lateral velocity, this means that we do the characteristics of the whole tire. And then once we have this data, we do a normal fitting with like purely linear fitting, nothing, let's say, based on, let's say, on neural networks or something else. This seems to be, let's say, enough in our case and acceptable.
I think that answers. And if any of this process, identification process, ever made it to a paper of sorts, that would be nice to know. So then the next question we have is about the modeling itself. Why using the single track model instead of a full 4-tire model? Is it that the size of the model is increased?
No, the size model doesn't increase too much. In some cases, if you, for example, include the wheel slip of the tires, yeah, that will put a higher, let's say, states. The issue is about the stiffness of the problem. This problem will start to be stiffer. So for also the optimization, so you have the same states and inputs, but the combination, let's say, of the tires will create a stiffer problem, which makes some problems for the final optimization. So basically, you will need reduce, let's say, discretization time and steps, and this will be create some difficulties.
Okay, and last question so far. This one is mine. So you briefly mentioned linearization at the beginning of the talk, and then you showed a little diagram where you said that for your specific setup you were using HBIPM. I was browsing quickly, and it seems to be geared or tailored towards quadratically constrained QP project problems. So how did you go about relaxing the problem? Is it just linearization, or are there more things that play? Because one thing that we found, a part of the reason we've resorted to at times other sort of solutions like pursuit, is that the full scale models, even the fully analytic ones, are too nonlinear, and then we need to resort to solvers that are too expensive and that we can not for our life run at those rates. So yeah, that's my question. Is it just generalization?
Yeah.
Is there any other special sauce?
Yeah, no, basically, yeah, it's about linearization. And as I said before, also, it's a combination about the linearization that is not done in a certain precise point, because sometimes you can read about linearizing around a certain point of region, but the particular aspect is to linearize it through the whole horizon, through the whole solution, the previous solution, the MPC. So basically, you do you start, for example, without any initial guess in previous solution. You do the optimization, you have your new solution, you use that solution as an initial guess for the next step, but not just for the optimization, but also to do the linearization over that solution. So for each step, you do step by step, at each stage of the horizon, a different linearization. So this way you have a linearization over the whole horizon, and this makes the linearization more accurate. But still you have it linear, so everything is linear. The other aspect is not just this, but also, as I said before, it helps a lot to have the reference and keep the problem close to the actual state, close to the solution, to the optimal solution. This helps a lot to reduce, let's say, the difficulty of having this kind of non-linear problem that is solved through a linear solution. Yeah.
I lost my camera. There we go. Different camera. We have another question. Why do you need regularization of the rear slip? Will MPC tend to drift a lot without it?
Yeah, of course, because you need to consider that the MPC it's quite something that sometimes we forget about it, but it's not that different from a neural network that you train it. You have your metrics, and you give, let's say, something that you give, let's say, more weights on it. So basically, if we say just follow a certain racing line, and you have like a certain error, and you also have like the real wheels that have the traction, you can, let's say, some the traction, but also, let's say, tend to have more oversteer, can use, let's say, more the tires, or even, let's say, in the turns, for example, can do a turn with higher, let's say, oversteer. So basically it doesn't have a particular regularization part in order to not just go to the performance, but also to let's say balance the effort of going on it. So yeah, practically it's something that it happens. For example, also the yaw rate, we have also regularization on the yaw rate. So for example, if we go on a curb on the racetrack, you have a noise, of course, state, a noise feedback, and having a short, really brief, really, let's say, short amount of weight on the yaw rate will have to not have, let's say, updraft change of direction. So yeah.
Wonderful. And another question came up. This one is a little bit more meta. Going further to full integration, and regarding the specific different testing scenarios, like overtaking, like an overtaking maneuver, do you rely on any sort of simulator, commercial, open source, custom made, for testing the whole thing, or do you go on hardware directly?
Yeah, no, we really massively rely on simulation, different level of simulation. And now, at the moment, after I would say 4 or 5 years of experience, we've been able to have a really accurate model of the vehicle simulation. We rely on a multi-body simulator based on Daimola. I don't know if you know it. It's based on Open Modelica language, using some licenses and libraries from Claytex, which is a UK-based company. They are really strong on this kind of aspects on Daimola. So through, let's say, I think 4 or 5 years, we started just modeling the vehicle in as a multi-body in the multi-body simulator and making it run just offline because it was too heavy. Then we tried to make, let's say, some simplification on it and trying to improve the model. And nowadays we are able to run it online in our laptops, and we model everything. So the tires, the suspension, everything detailed. So we rely on that. And basically it's a full cycle that starts from getting the data from the real world, or better, let's say, start at the beginning from this initial guess of the multi-body simulator, because of course we have some knowledge of the components, for example, the engine, the wheel, and the tires and so on. They are not accurate, but we had an estimate. We fit the model on this simulation. Then we go on the real world. We do the experiment. We get the data, and this is a full cycle that is moving on. And also for but this is, let's say, more about the performance, so like single vehicle. Instead, for multi-vehicle interactions and so on, it's really difficult to have your custom-made simulation. We rely on some racing games. We made a paper on Assetto Corsa, which is a very, very well-known racing game, that we created some interfaces to that, and we basically been able to run autonomously the cars and also interact with the other cars and so on. That's, let's say, a really cheap solution. And then there are also, during the competition, we have also some other commercial simulators created, let's say, by other companies, where we can simulate with the other teams. Let's say that we have this, our custom-made solution, custom-made simulator with the multi-body model is the more accurate. It's really close nowadays, and this helps us also to experiment maybe for the future for reinforcement learning-based solution and mixing between reinforcement learning and MPC, because in the real world it will be really difficult to test directly. But we still, let's say, have using also other simulator in order to simulate about the planning and etc.
Wonderful. And we are about on time, but I still have 2 questions that I want to ask.
Yeah.
So if you don't mind, so you said that part part of the reason why you're successful with this faster, relaxed chronometric formulations is that you're providing a reference that is reasonably close or in the neighborhood of the optimal solution. My question is, are you computing this offline or online? And if you're doing it offline for whatever reason, how do you factor in the overtakes? I presume it's the former. You're doing it online.
Yeah. Basically, let's say that we do several steps. We do offline a high level, let's say, reference. For example, in our case, a global trajectory on the track that we know more or less the optimal path, not the speed profile, but the path more or less, you know it offline, and that's starting one thing. And then the speed profiles, for example, to generate this that you can put and you need to follow by give to the car, to the MPC. What we use like some online, some simplified models, like for example a GG diagram, which is a point mass model that more or less, let's say, follow a certain characteristics of the vehicle, that it's easier to model without any optimization, but just with like backward and forward execution. And then we find, let's say, a good solution, a good speed profile that it's really close to the physical one. So we give this in this way. This simplify about the longitudinal. This helps a lot for longitudinal. The other aspect is, as I said before, that we don't give a reference that it's too far to the MPC in that certain time horizon. So we do also some discretization and we don't, let's say, we resample and so on. About the overtakes, which is, let's say, the part of the lateral, we combine heuristics, let's say not let's say optimization based, but heuristics part with a high level planner, which is I will share, let's say, some references later. We just a colleague of mine published the paper and presented at IROS, where we do high level planning, where we simply use the forecasting, the prediction of the other agent and our prediction of the MPC. And we find the potential interaction in the future, in the horizon, and we create some two tunnels, some viable tunnels, different ones. And then just with a really normal function cost, so without optimization, we select the best tunnel, and we give that tunnel as a soft constraint to the MPC. So basically, the MPC has a soft constraint in order to move into the tunnel with a certain speed that it's followed using, let's say, that simplified GG planner online. And this helps us a lot because the MPC already knows, basically you're saying not all the track, but just a restricted part of the track. With this already guess about the speed profile. We have also other further, let's say, tweaks that we'll also publish soon.
That's clever. And my last question, and it goes back to the name of the talk about reduced order models. Throughout the presentation, it seems that you arrived to a sensible model that affords real-time MPC control by principal analysis. My question is, have you attempted to replace that principal analysis with data-driven models, and even more so, dimensionality reduction techniques on that learned model? Maybe not. Maybe the single track solution is good enough.
Yeah, we never experimented. It's something that we would like in the future. We have in our mind to try to experiment also on that point. But from the last research and the last state of the art, there are several works. There are other works from Stanford, and some work also from our side that demonstrate that this kind of model is almost enough. It's really close to have really good accuracy. So in the first video that I show you, the overtake to Tuman, etc., that we were really close to the human performance. We control the car with 30-40 centimeter of error. So basically, you're going at the limit with really negligible error. So that it's enough. But what is not enough is potentially the solution in order to find the parameters of the tires. so the parameters of the model. So in that part, there are a lot of research going and already some good solution in order to find the parameters online. We have some, let's say, solutions. So basically, we also use online the same things that we are using offline. So like getting the data, trying to fit in online, having new parameters and applying it, something like that. But let's say that the research from my side, it's more about this model, it's okay. But the parameters that we put in particular the tire models, are not always that good and will be great to mix, let's say, like data-driven solution in order to find this part. There's also a lot of research also on removing some parts of the single track and just replace it to data-driven parts. But I mentioned Jan LeCun, where potentially in some cases, if you know the model good enough, there's no need, let's say, to change the physical and the model, etc. But it's an advantage that you have. You know more or less how the physics works, but maybe you don't know the exact values. And those values, maybe you can find them with data-driven machine learning solutions.
Wonderful. I think we have no more questions. I, for one, don't have any more questions. And we are 10 minutes over. So if there's nothing else, I want to thank you, Ayub, for the time, for being here. It was an amazing talk. And
thank you.
Yeah.
Thank you. It's been a pleasure, and really happy that I also had a good feedback from question and everything. So feel free to keep in touch, search from my works. If you have other questions, just contact me. I will be happy to reply and give you references and so on.
All right, amazing. Then I think it's our time to go. Thank you all.
Okay. Thank you. Bye. Bye.
Bye bye.